for the introduction. So in this talk, I will introduce an optimization techniques we developed for model checking Petri nets, and in particular for the reachability problem. And on the top of this optimization technique, we develop a quantifier elimination procedure to solve specific problem for which we are interested in. So first of all, my talk is about Petri nets. So Petri net is a mathematical modeling language for concurrent system. So basically a net is composed of places that can represent some shared resources. For instance, here we have some task on disk to execute and some free memory segments. It's a net for that model a small operating system. And the places can contain some tokens that represent in which state the system is. And in the Petri net theory, we call a state a marking. And of course, a system can do some actions over time that are represented by transitions. And the transition is enabled when we have at least one token in all the input places. And if we fire the transition, we will consume one token from the input places and produce one token to all the output places. So this net is from the model checking contest, that is an annual and international competition for model checking tools. And as I said, it represents a small operating system. The particularity of Petri net is that it is a kind of infinite state system verification, because the net is not necessarily bounded, and we can have an infinite number of tokens contained in the places. And it's like an assembly language for concurrent systems. And for instance, there are a lot of description languages that are compiled to Petri net. So it's quite interesting to study Petri net. So in my work, I'm interested in the reachability problem. That is for instance possible to reach a marking from the initial marking such that I have more tokens in the place executing tasks than in the place task on disk. And the issue comes from the state space explosion. For instance, this small net has about 10 at the power of 17 reachable markings. That's quite huge. So we need some optimization technique. So the problem that we are interested in is the reachability problem. For instance, is a linear predicate f reachable, meaning if there exists a reachable marking that satisfies my predicate. And the dual problem is the invariance, the check of an invariant, meaning that whether all the reachable markings satisfies the predicates, and to check that predicate f is an invariant, we just check that it is not possible to reach a reachable marking that violates our predicate. So using reachability properties, we can encode a lot of different properties, such as the coverability of a given marking, meaning can I reach a state that is greater than a given marking? We can also check the reachability of one exact marking. We can check that some transition is quasi-live, meaning I can reach a state such that the transition is enabled, or I can check that my system is deadlock-free or has a deadlock. A particularity of Petri net is that we can use linear predicates to encode the semantics, and so we have the same formalism for semantics and properties. For instance, we can have a predicate enabled that is true at marking m when the transition t is enabled. And we can also encode using the linear integer arithmetic theory a predicate t that represents the transition relation, and that is true at marking m prime if I can reach marking m prime from a marking m. So since we can encode the semantics of a net using this theory, we can use some SMT methods to perform the model checking phase. So in my talk, I will present a previous optimization technique that we introduced in my team, that is polyhedral reduction. I will present a specific data structure that is called token flow graph. And on the top of token flow graph, I will present to you a quantifier elimination tailored to the specific kind of constraints that we handle. So first, polyhedral reduction. So here we have this small operating system net, okay? I just renamed the places and the transitions to be much simpler. And we have a reduction of this net on the right. And we obtain a Presburger predicate that permit to reconstruct the state space of the initial net from the state space of the reduced net. Our Presburger predicate has always the same form, It is an existential formula with a conjunction of equalities and inequalities. And so from the state space of the reduced net, we are able to reason on the state space of the initial net. So we have the equivalence between both nets. We can also define an equivalence between markings, and we say that marking M1 from the initial net is E equivalent to marking M2 from the reduced net if they are solution of E. Okay? A necessary condition is that they must be equal on the common places, because we can have some place that is both in the initial net and in the reduced net, such as the place P0 here. So before introducing the notion of equivalence between nets, I will give you two key results of this polydroic equivalence. For instance, we can check using our polydroic reduction that predicate is reachable in the reduced net. If in the reduced net I reach a marking M2 prime, okay, that is a witness of a given predicate, I know that for all the corresponding solution M1 prime in the initial net, they are also reachable. So if I find some counterexample, I know it is a relevant counterexample in the initial net too. We can also check invariance, because if there is some counterexample of an invariant in the initial net, I know that there exists at least one corresponding marking M2 prime in the reduced net that is necessarily reachable. So here you have the definition of our equivalence between nets. So the first condition is that the initial marking must be solution of E and compatible. If we take any reachable marking either in the initial net or in the reduced net, there must be solution of E. But the most important conditions is this one. If we take any pairs of marking M1 prime and M2 prime that are solution of E, M1 prime is reachable if and only if M2 prime is reachable. So we have the equivalence between the reachability set of the initial net and the reduced net. So here you have another example. It's a model that represents a landing gear of an airplane. So the net is quite big, and we can reduce this net using some structural reductions in the net on the right, and we obtain a linear predicate that contains about 400 variables and literals. But there is another version of this net, and with the linear predicate that contains 30,000 variables and literals. Okay, because the initial net is quite big. So imagine we want to check that the formula F1 is reachable in the initial net, okay? So we will take our example of small operating system for the rest of the presentation. What we propose in the previous work is to construct what we call the E-transform formula. That is, so we have some variables that represent the place of the initial net, say P1. We have some vector variable that represent the place of the reduced net, say P2, okay? And we assert we have an existential quantification on the variable of the initial net. We assert our predicates that permit to link both state spaces, and we assert our predicate of interest. So if I put in red the variables from the initial net and using the letter Q, and in blue it's the place of the reduced net. So here you have an existential quantification. The predicate E may contain some existential quantification too. We have our predicate E that permit to reconstruct the state spaces. And when we have a place that is common in both nets, we assert the equality between the variable from the initial net and the reduced net, and we assert our predicate L1 that we want to check that it is reachable. And so we have a problem that is much simpler, that become is the U-transform formula F2 reachable in the reduced net N2, and since the net is smaller, model checking performs better. So we have this theorem that F1 is reachable in the initial net N1 if and only if the E-transform formula is reachable in the reduced net N2. But there is an issue, is that F2 contains some existential quantifications, so it is a Presburger formula with existential quantifiers, and it is not suitable with random exploration, because when we randomly fire some transitions and visit states, each time we visit a state, we need to solve a Presburger formula, and it's quite complex. And it is not also usable with standard model checkers and standard model checking techniques because they only support quantifier-free formulas we support on the net that we want to verify. And here we have Presburger formula with quantifiers. So we need to introduce a procedure to eliminate quantifiers in our E-transform formula F2, and the problem is X space in general for existential formulas as the fragments that we target. But why we do not use standard elimination procedures is that this procedure often requires the use of a divisibility operators that is called the straight format sometimes, and it is not part of the logic fragments that we target. And also our formulas often involve several hundreds or sometimes thousand variables and literals, and the state-of-the-art methods do not scale to this number of literals and variables. So here we have Octant, our tool. Okay, it's the number of computed predictions given a time limit, and we compare our procedure to the best performing tools for eliminating quantifiers. And what we see is that our tool and our method for the specific kind of problem we handle is able to project like 99.5% of formulas in less than 1 minute. And ISL from the Barbina toolbox and Wellog are not as good. And using ISL, we can just eliminate quantifier in 61% of formulas in less than 1 minute, with a time limit of 1 minute. So to perform our quantifier elimination, I will introduce a specific data structure. So if we take our initial net, our reduced net, our Presburger predicates that permit to link both state spaces, we want to reason on graph instead of solving Presburger formulas. And precisely we want to capture the particular structure of constraints that we have. And so we introduce a directed acyclic graph with two kinds of arcs. So basically, we have one node per variable and per constant, and we have two kinds of arcs. The first kind of arcs represents what we call the redundancy equations. It means that we remove the place P1, and its marking is always equal to the sum of the parents. So it's the first kind of arc that we have. We have the same here. We remove the place P6 from the net, and we can reconstruct the marking from the sum of the parents. And we have another kind of arc that are called the agglomeration arcs. So it means that we remove the place P7 and the place P8, and we introduce a new place, the place A1. And so the number of tokens contained in place P7 and P8 must be equal to the one in A1, for the sum of the number of tokens. So here the sum of the children must be equal to the parents. And any distribution is reachable in practice. And we have the same here for A2. P5 plus A1 is equal to A2. So you can remark that if we forget about the constant, the root of our graph is exactly the place of the reduced net. And so now I will just give you an idea of how our quantifier elimination procedure works. I will not go into the details too much. But imagine we want to project this formula, and what we want is a formula F2. Okay, we support on the reduced net, so we support on the roots if we forget about constants, such that F1 is reachable in the initial net N1 if and only if F2 is reachable in the reduced net N2. So I put the formula in a kind of normal form, okay, with the left-hand part greater than 0. And so we want to maximize the left-hand part. So when we have some redundancy, it's quite simple. We can just substitute, for instance, the place P6 by the sum of the parents. That's easy. I just rewrite the formula. I can do the same thing for P1. I can just replace P1 by P4 plus 496. But it's become complicated when we have some agglomerations. Okay. So we introduce a concept of polarized literals, it means that we look, okay, so we have the agglomeration A1 is equal to P7 plus P8, and we look at the variable that has the highest coefficient in all the literals. And here P8 has the highest coefficient in both literals, so we say that the literals are polarized according to the agglomerations. And so it means that to maximize the fact to be greater than 0 in the left-hand part, we can put all the tokens in place P8. So we can just forget about P7 and replace P8 by A1. So we obtain this literal. And we can do the same thing with these agglomerations. Because A1 has the highest coefficient in both literals, we can just forget about P5 and replace A1 by A2. And so we obtain these literals. And we obtain our formula F2 with support on the reduced net, with support on the root of the graph. In practice, sometimes the literals are not polarized according to the agglomerations. So our procedure can obtain an under-approximation or an over-approximation. If the under-approximation is useful to find some counter-example, it means that if we find in the reduced net a witness, okay, of our projection, we are sure that there exists a witness in the initial net. So it's useful to find that the formula is reachable. And the over-approximations, it's useful to prove some invariance, because if a counterexample exists in the initial net, we are sure that this counterexample exists in the reduced net. So if we prove that a predicate is an invariant in the reduced net, we are sure that the predicate is an invariant in the initial net. But in practice, 80% of the formulas in the model checking contest, in the reachability category, are polarized according to our agglomerations. So we don't use a lot these approximations. So now we will have a look at some experimental evaluations. So I will just recall the workflow. We have a net that we want to verify. We reduce it into a smaller one. We obtain some Presburger predicates that permit to link the state space of the reduced net with the state space of the initial net. We construct a graph that is a token flow graph. And given a reachability formula, we are able to project this formula into a new formula that has its support on the reduced net. And now we can apply any model checking method or any model checking tools. For instance, we can do some random exploration, induction, or we can use TAPAL. And so we performed some experiments with TAPAL, who won the model checking contest in 2022. And so what we observed is that on the challenging queries, meaning that is a query for which at least one tool failed, because there are a lot of easy queries that are easily solvable by all the tools, we observed that the projection permits to compute more queries using TAPAL. So our optimization doesn't overlap too much the optimization that are already done in the best performing tools in the model checking context. And so we participate with the model checker in the model checking contest. The model checker is called SMPT. So we did 3 participation since 2021, and we applied our quantifier elimination procedure in 2023, okay, just here, and it's permitted to compute like plus 5.5% more queries between 2022 and 2023. In 2022, we applied polynomial reduction, but just with the heat transform formula, just using the formula with existential quantifications. So just to finish, our quantifier elimination procedure, we define a quantifier elimination procedure that is tailored to the particular constraints that we handle in polynomial reductions, and it permits to combine polynomial reduction with any model checking technique or tool. And our experiments show the effectiveness of our approach, and also it permits to demonstrate that it does not overlap too much other optimization techniques in best performing tools, such as the use of slicing or the use of symmetries, for instance, and so on. Thank you very much for your attention.
Thank you very much. You stayed perfectly in time. Questions?
I have not really understood the difference between quantifier elimination in your case and the case of polyhedra like used in the static analysis.
Yeah. What we do, it's like just quantifier elimination, the same thing.
Oh, okay.
Yes, there is no difference. In practice, we can use any existential quantifier. We can use any quantifier elimination procedure. It will work, okay? But what we observe is that the best tool were not performing so well for the problems that we handle because we have a lot of literals and a lot of variables, like thousands of variables, thousands of literals.
If I understood well, you manage banded Petri net?
Banded and unbounded.
Banded and banded.
Both.
Both. Okay.
Yeah.
Okay.
We do not have any constraint on the weight of arcs. We don't have any constraint on.
And do you know all the very old work on reduction of Petri
from
net?
Bertolo?
Yes.
Yeah. Okay. The idea how we compute polyhedral reduction is by applying structural reductions iteratively, and some rules are from Bertolo, and they are a little bit modified to have this Presburger formula.
Okay.
To link both cases, but it's the same idea.
Okay.
But for instance, Yancy Remig used reduction from Bertolo in ETS tools and other reductions. And what he did is that it looked at the support of the formula, and he doesn't reduce any places that are in the support of the formula. Here, we just reduce the net, and we look at the formula just after.
Okay.
We can reduce what we want, since we have our Presburger predicates that permit to reason on this statement.
Okay. Okay. Thank you.
Oh, the correspondence between the original and reduced, is it some kind of bisimulation or?
It looks like, okay,
Yeah, it looks like,
but it's not.
It's not.
Because you don't have the bisimulation for all the reachable markings, because sometimes you can do some irreversible choices, for instance, with the agglomerations. So we recently proposed an automatic method to prove that an abstraction is correct, and we talk about this point in this paper. So, but it looks like, but it's not.
And it's crucial that you use conjunctions here, or could you also use disjunctions for the reduction?
If you want to use disjunction, we need to have the formula in the DNF. So here I have a conjunction, but we work cube by cube. But since the algorithm is linear on the side of the token flow graph, even if we have an explosion during the DNF, it's not a big problem because we are able to project like all our formulas.
Any more questions? No question? Then thank you again.
Thank you very much.